Okay, so today we're going to look at this particular reaction graph, and we can see several things that are occurring. The first thing I want to put your attention to is the fact that the fact that I have a start point. And the start point that I'm looking at is time 0. What can you tell me that's present in time 0? Do I have a lot of red or do I have a lot of green? I have a lot of red. And how much green do I have? I have no green. It's actually at 0. What this tells me then is that when I have a reaction that looks like this, two NO2s can become N2O4, you'll notice here that specifically that the arrow points to the right, but there's no backward arrow. Why is there no backward arrow? Well, in this situation at time 0, I have no green. And since I have no green, none of the green can turn into red. There's no backward reaction. Which direction do you think is faster, going to the right or going to the left? Right. Going to the right. That means at the next time period, I should see more green and less red. Does that make sense? Let's take a look at the next time period here. So I'll call this time 1. And you'll notice that the green has increased and the red has decreased. What does this mean? Well, if I were to draw another snapshot here of the equation, you'll notice that the arrow that goes to the right has gotten a little bit shorter. But the arrow that goes left now has a tiny little arrow. Why is that? It's because now I have some green. I don't have a lot of green, but I have enough that some of them can start turning back into red. Are the arrows equal in length? No. One direction is still faster than the other direction. Which direction is it? To the right or to the left? To the right. Which means that green will continue to increase and red will continue to decrease. Which brings us to our next cut point. Okay, our next cut point is now really interesting because the amount of red and the amount of green is actually equal. If you look at this little dot right here, this little section here, it turns out that I have the same amount of red and the same amount of green. But when I look at this section here, what do you notice about the arrows? Are they the same length? No. This implies that there's not going at the same speed, even though I have a lot of green and a lot of red. I have the same amount of red and green. So why are they not going at the same speed? Well, it turns out that sometimes you have a reaction where the hill is not equal, which makes it easier to go one direction or the other direction. I want you to imagine that I have 3 skateboarders on each side of the hill. What can you tell me about the number of skateboarders on each side? Same number of skateboarders. This is a lot like this position here. I have the same number of green and the same number of red. Questions for me? Okay. If I were to ask them to get over this hill, do you think the same number of skateboarders will be getting over the hill every hour? No. One direction is faster than the other direction. Which direction? Going to the right because it's easier because of the smaller hill. Does this make sense? So this means that over time, this should still continue to decrease. This should continue to increase. So let's check the next checkpoint here. At this point, what happened to the amount of green? It went higher, and the amount of red went lower. At this point, what do you notice after these little like blue circles? What happens to it stops changing. The implication here then is that we've reached a point where they are now the same speed. The same number of skateboarders are going over the hill in 2 different directions. So if I come back an hour later, I still see the same number of skateboarders on each side of this hill because they're moving at the same speed. So how do we know equilibrium has been reached? We can see that these concentration lines have reached a flat point. And that flat point tells me that it is no longer changing. It's no longer increasing, and it's no longer decreasing. So we know that we've reached equilibrium because we've reached these flat lines. At that moment in time, our forward speed and our backward speeds have now reached the same speed. This is a lot like the fountain, where water flows downwards into a bowl and water flows outwards out of the bowl. And as long as they're moving at the same speed, it'll look like nothing is really happening, even though the water still is moving. Questions? A lot of people can maintain their weight, meaning that if I weighed them next year, they still weigh the same. Okay? Does that mean they stopped eating or drinking? No. So how are they able to maintain their weight? Because they're putting things that are heavy into their body. They must have an equilibrium where the things going into their body is exactly the same as the things going out of their body. Does this make sense? Yeah?
Yeah.
Okay. Let's move on.
Like the forward rate is the food? Like it's what's going...
Sure, yeah. You can think of the forward weight as food going into your body, making you heavier. And then you can think of food going backwards as kind of like food going out of your body. And as long as they're the equal rates, then you can eat as much as you want, as long as it also goes out.
Oh, okay.
Right?
Yeah.
Okay. So I'd like you to take a look at these three graphs. They're all different kinds of reactions. And I'd like you to come up with 2 similarities and 2 differences with a neighbor. Ready? Go. So we can make a few concluding statements here. In every situation, we have a different starting point, but all of them reach equilibrium when they reach these flat regions. And so it's where this little gray line delineates. And so if I give you a graph, all you have to do is look for those flat regions, and you know that that's where equilibrium actually occurs. Great, which is right there. Any problems with this? Okay, so today's big lesson happens to be this dude here. He's French, and so we pronounce his name kind of funny. Anyone have any idea? Yeah, that's very, very close. His name is Le Chatelier, all right? And Le Chatelier sounds like this because a lot of times French words that start with CH are pronounced SH, right? So like chateau, chandelier, Chanel, okay? These are things that are French, that have a French origin. Champagne, okay? Now, Le Chatelier actually has a pretty specific principle, and this is Le Chatelier's principle. If we have a system that's in perfect balance, equilibrium, and I mess up this balance by applying a stress, okay? I'm going to highlight that word. This change is often referred to as a kind of stress. It means that there's something that is kind of messing up this equilibrium. When the stress is applied, what happens is the system will try to shift in a way to do the opposite of the stress, to minimize the hurt, if you will. And so it always shifts in the direction that does the opposite of the stress. It helps to cancel out the stress. So, there are 3 different ways it can shift. The first direction is called forward. That's to the right. All reactions are written in a forward and reverse reaction, and so by default, we think of left to right as the forward reaction. We can also shift in the reverse or backwards direction, which is to the left, or we could have no change. This is sometimes possible. So these are essentially the 3 options. So on a multiple choice test, you would have these 3 options. Now, why would something shift in this direction? Oops. Let me give you some time. Okay, so in my made-up example, I'm going to pretend that I have an equation that looks like this. I have money on one side, and then I have an arrow where I can change this into stuff. Okay, I'm being very generic about this. Can you change money into stuff?
Yes.
How?
Buying.
Buying. Okay. Now, I'm going to draw an opposite arrow where you can change stuff into money. And how do we do that?
You sell things.
You can sell things. Okay? If this is in equilibrium, what does that mean? Your selling and buying are canceling each other out. Meaning that the amount of money you spend buying things is the same amount of money you get from selling things. So over time, you should have the same amount of money. It should read a flat line. And you should also have the same number of stuff. It could be different stuff, but it should be about the same amount. Are we okay?
Yeah.
So over time, nothing should change. This is an equilibrium. Are we okay with this idea?
Yeah.
Now, once it's reached this equilibrium, I can actually mess up the equilibrium by applying some kind of stress. So let's pretend this is a stress. Let's pretend that you got robbed. Okay? And they basically took your money. Okay? So money was lost. What is the opposite to losing money? Gaining money, specifically. So the opposite is gaining money. Which direction will get us more money? Shifting to the... Which way? Left. When you shift to the left, you're basically selling some of your stuff to get money. But why? Because the stress was we lost money. Our goal then is to minimize the pain here. We need to sell some of our stuff. So if you need money badly, then you have to sell some of your stuff. When does this stop? When does the selling stop? When you reach a new equilibrium. You'll reach a new balance point. Are we okay with this idea? What if I applied a different kind of stress? What if I tried something else? What if my stress this time was you were given lots of stuff? So you inherited stuff. Your brother went off to college and he's like, here's a bunch of stuff. Are you in balance again? No. You were in balance perfectly before. Now you have too much stuff. What's the opposite of more stuff? Less stuff. And which direction of shift will get you less stuff? To the left. You're going to sell some of your stuff. You get a little bit more money. And when does this stop? When you reach a new equilibrium. And so you have to shift to the left to use some of this extra stuff. It is the exact opposite of the stress. Questions? Let's try this again. Your turn. Let me erase this. Here's your stress. You won the lottery. Okay? It's a stress because it messes up your equilibrium. You have no longer a balance point. It's no longer. I'd like you to talk with your partner about what is the stress and which direction will it shift to balance out this new stress. Go. So, winning the lottery means more money, which means that we need to do the opposite to the stress, which is less money. And the direction of shift will be to the right. We need to shift to the right to use some of that money to buy some stuff. Okay, so I'm going to give you an example. And the way the example is going to work, I'm going to have A, B, C, and D. And I'm going to tell you that this specific reaction is in equilibrium, meaning that two A's and one B's are turning into C and D are turning back into two A's plus one B. And we're going to create a kind of graph to chart what's actually happening. And so the way it's going to work is I'm going to start by dropping a stress in this first column, and then Le Chatelier is going to predict that we're going to shift in the opposite direction. And so what we're going to do is we're going to actually write out.
Are we writing this?
I'd like you to make a table. So Le Chatelier is going to predict that the opposite will occur. So we're going to help chart out the result of these stresses. Okay? So I'm going to drop a stress here. The first thing that I'm going to tell you is that I'm going to increase the amount of A. When I do this, it's going to actually mess up my equilibrium. What I want to do is I want to shift in the direction that accomplishes the opposite to the stress to help make the stress less painful. What is the opposite of increasing the concentration of A?
Decreasing.
I want to decrease the concentration of A. It'll become less painful or have less of an impact. This is why when your grade goes down, when you take a test, that's a stress. Your grade went down. And so you try to counter that stress by doing the opposite to make your grade goes up. And so I'll oftentimes get questions like, hey, can I do any extra credit? Because intuitively you know, since your grade went down, you want to minimize the impact this test has by doing some extra credit to counter the negative score that you got. Does that make sense? So we want to try to do the opposite. And in life, you want to achieve this kind of balance. Which direction of shift will accomplish the opposite to the stress? What kind of shift will do the decrease in A? It is to the right. The shift to the right will decrease the amount of A. But it has some other effects. When we shift to the right, not only does A get used up, we also use B. And so the net effect here is that not only does A go down, but so does B. And then something else happens. When we shift to the right, A and B get used up to do what? To make into C and D. And so it turns out that C goes up. Okay, Mr. Chen, what happened to D? Well, D happens to be a liquid. Things that are liquids and solids actually do not go into this chart. The reason for this, I don't want to tell you just yet. Okay? But if you see a liquid or a solid, you can ignore it. Questions for me?
That hurt.
Okay, which direction of shift will accomplish the opposite to the stress? I want to shift to the left. When I shift to the left, then I will increase the amount of B that should help cancel out some of the original stress. What are the effects of shifting to the left then? It should be exactly opposite of shifting to the right. A and B should go up, and C will go down. Okay, let me give you a new stress. And this is to decrease the amount of C. I would like you to figure out what goes in the entire row, or you can work with a partner, but I'd like to give Diego one more chance. What do you think should go in the next? This slot here. This slot here? No. You'll have to wait. Okay. Are you ready? Here we go. I have increase in C, which is the opposite to the stress. Which direction?
Forward.
Forward to the right. And the net effect is A and B go down, C goes up. You'll notice that when we shift a direction, whatever direction it is, if it's to the right, then the left side decreases and the right side increases. Right? Because that's what's happening. There is one last one, and it is to increase the amount of D. I'm going to give you the answer to this one. The answer here is no change. No change. No change. And the reason is because it's a liquid. And so anytime you see a liquid or a solid, it actually doesn't participate in this type of Le Chatelier's principle. We get this no change. So liquids and solids.